for today, this will be due Tuesday at midnight. We have Lab 10, and Lab 10 is on oscillations. So I've, as always, put the handout, and there's also a second file on the data. Now, how this is going to work, I don't care if you do it with your lab groups and just turn in one, as long as you all have your name on it, or if you do it by yourself. What I want you to do today, when I go through the handout, I'll explicitly tell you what should be on there. But for now, if you want to create a Word document, just a blank Word document, that'll be useful just as a place to put your graphs for now. So just open a Word document when you get the chance, and we'll put the graphs there. So what I did for this lab is I took my IOLab and my dog is being annoying, and using the long spring, if you anchor it somewhere and pull it down and let it go up and down. Obviously with my hand, it's not doing it as well as it should, but what ended up happening is you get this really nice sinusoidal curve of the motion, of the acceleration. So if you want to do your own data, that's okay, and you include this graph, but you don't have to, or actually don't do your own data. I think I originally was going to let people do their own data, but don't do it, because I put the, I gave you the data for this. But what you see here is the acceleration of the IOLab. Now keep in mind, the IOLab was going up and down in the Y direction. And that motion is sinusoidal. Sinusoidal meaning it can be described by cosine, it can be described by sine. I'm going to actually open these in the actual documents that I have here and here. So what I did was I suspended it, I let it go for a bunch of periods, and then I downloaded the data file. And that's that other file that you have here in the module. So for now, what I want you to do is go to the Osci oscillation data XLS spreadsheet, and you'll find that the data is here. What this data actually is, if you ignore it all for a minute and look at just A and C, column A and column C, column A is the time of one period. So what I did was I looked at this, where did you go? Sorry. I looked at this and I went from about 1 second to 2 seconds. Now let's stop and think about this for a minute. So anytime you have a sinusoidal periodic motion, the period goes from crest to crest. And what I want is I want the data of one period. So from this crest to this crest, I want that data. Once I have that, my ultimate goal is to get the equation of motion. And when we do oscillations, our first step is we want the equation of the motion. So we're going to describe this motion by this y equation, which gives the y position of the IOLab as it moves up and down. Now, in your book, it's given as an x equation. We're going to give it as a y. And the equation is the amplitude or maximum value times cosine omega t. And remember, this omega is not the same as circular motion omega. It is the frequency angular velocity, which means it's how the cosine, wherever that stupid thing went, it's how this cosine varies with time. So it's the angular velocity of the cosine function. And our goal whenever we do oscillations is we want to find Y max, we want to find omega, and we want to find the phase angle. And we'll get all of those things from our graph. What we're going to do is we're going to take our data here. We're going to get one period, and then we're going to find the amplitude, Y max. We're going to find omega, and we're going to find the phase angle. And then from that, we'll graph various things. So the first thing I did was I looked and I said, okay, a period goes from 1 to 2 seconds. Specifically, in the data I've given you, the period starts at 1.07 seconds, and then you need to go down and figure out where the period ends. I'll help you with that right now. How you can find that is notice that the acceleration starts at a maximum of about negative 3.9 or something, goes to a maximum of negative 16, back up to a negative 3. So when I look at my data, I can see that as I go, the acceleration in column C starts at negative 3-ish. And as I roll down, negative 10 gets to negative 16, starts heading back the other way. And I want to look at when it gets to a minimum. And it looks to me like right around this point right here, which I'm going to highlight. At about 1.9234 seconds, it starts the period over. The motion starts over again. So we're going from about 1.07 to 1.9234. The rest of this data, you can just delete, just cut it, make it go away. You don't need it. Ow. Sorry, guys. Fire warning. So now we have, just paying attention to column A, we have the time of one period. Now what I've done, I've created for you column B, and all column B is the adjusted time, where I've subtracted off 1.07026 seconds from column A. So now I can just completely hide this. So this is now, column B is your time for one period starting at a time of 0. And when we look at this, we can see that it goes to 0.85321, and that's important because the first thing that we want to know is we want to know omega. Now omega is 2 pi over the time. And when you go through this, I should say, when we get down to here, it tells us what to do. We want to graph acceleration versus time if you wish. You don't have to do that. Then we want to find the period starting at a time of 0. We've just done that. So using the data of the first period, we calculate the time starting at t is equal to 0. Part 4 is find the angular velocity, omega, and we have this chart. So the time of the period is 0.85321 seconds. That is the time in column B that we normalized to a time of 0 to start with. And we chose kind of around when we thought that crest ended. So in this data table, which you will turn in your final thing, the period here, I would write 0.8532. I guess, seconds. Now, finding the angular velocity. If I know the period, I can always find the angular velocity from omega is 2 pi over t, or t is 2 pi over omega, whichever way you want to see it. So take 2 pi and divide that by your period here, and that is your omega. If I do that, 2 times pi divided by 0.85321, I get 7.364, and we can leave it at that. You can put 2 if you want, rad per second. So now going back to this, we now have omega. We have the first of our three variables that we want to find y. However, what this thing was doing is giving us, this data is giving us the acceleration. And if we go back to the free body diagram of the IOLAB, we see that there's a force of a spring, which remember, spring force is minus ky or minus kx, y in this instance because y is our position variable. We also have a weight, minus mg. So ma is minus ky minus mg. Divide through by m, we get this equation. If we move the g over, we get a plus g is equal to minus k over my. Now, technically, if we were to do this differential equation, we would actually forget about the g and solve this as a what we call a homogeneous equation. However, I'm going to assume that the acceleration is just a plus g. So we can find y. We can find our position from adding g to our acceleration and then dividing by our omega squared. And I want you to do that. So, and I want you to do it in 2 steps. So here in column E, all you have to do is hit equals C plus 9.81. And what that's going to actually do is it's going to rescale our acceleration. And you'll see that in a second. Once you do that in Excel, you can just drag down and it will fill in all the data. And you're going to watch me do this a little bit. So once we do this, if I graph this, and I'm not going to actually save this graph, but if I graph my acceleration versus time, eventually, insert, and all you have to do is make a quick scatter plot of it. I muted you, Ali. So this is our acceleration versus time. And if we look back at this, for this first period, we have the acceleration versus time now centered at 0. Okay, it's not perfectly symmetrical around 0, but it's centered around 0 and we have a cosine function. All right, we can get rid of that. Now y, as I said here, is actually a plus g divided by omega squared, where omega squared is k over m. So here what I want you to do is hit equals this column, E2, divided by what we got for our 7.3642 times 7.3462 y. Okay. Oh, I see why. What I want is E3. All right, and now drag that down. And it will fill in the y values. And so what this is doing is this is assuming that the motion is around y is equal to 0, and I'll show you that in a second. This is one of the graphs that I want you to keep. So once you have this, and you'll see this motion really fast. Eventually, So now hit insert a scatter plot. Make sure you title it. I don't care about the axes here, but I do want titles, and you'll see why soon. So what we have here, this is Y versus T for one period. It's the position of the IOLab centered on an equilibrium point that I am calling 0. We're going to have an issue with that later, but for now, we can see that this is one period of our motion, and we've centered it around some equilibrium point, 0. So we have that. Now, having that, we can now see that it starts at a maximum amplitude, goes to a minimum amplitude, well, it goes to 0, and then it goes to a negative maximum amplitude, and back to a positive maximum amplitude. So when we look at our Y function, we need to figure out what is Y max from our data. What I'm going to tell you you can do is you can take this, essentially, to be your maximum amplitude, if you want. We're going to assume 0.1189. Let's see what it is at the end. It's about 0.117. So let's call it 0.118 is our amplitude here. That's a little bit iffy. And why is it iffy? It's iffy because we have real data. We've got to kind of ballpark what was the maximum amplitude. I'm going to say it was 0.118. 0.1189 actually is what I'm going to say. So on my here, 0.1189 meters. Okay, about 11.9 meters. And now the last thing that we have is our phase angle. What the phase angle tells you is that if this is a cosine function, at time t is equal to 0, where does the function start? If our graph started here, the cosine function would not be at a maximum value. But we're starting at a maximum value when t is equal to 0. Now, I'm going to go to a really quick to a one of these and talk about this to make sure you understand this, because this does come up in oscillation problems all the time. So let's look at a couple different examples here. Imagine we have, like we have here, where we have a cosine function at time, and I'm sorry, I'm writing off to one side. So we have a cosine function at t is equal to 0, y is equal to y max. When that happens, we say that y at time 0 is equal to y max cos omega t plus or minus phi. I know it says minus in the lab. And then what is that equal to at time t is equal to 0? Y max. Since this is 0, we really get y max cos phi is equal to y max. Divide through by y max, you get cos phi is equal to 1, or phi is equal to cos, arc cos of 1. Well, when cosine is 1, the angle is either 0 or pi. But when it's, I'm sorry, 2 pi, we're going to choose the smallest angle. It could also be negative 2 pi. And I know that's not super important. But so our phase angle phi is 0 for our function. Now, if we had, let's say, as it shows in the max, negative max, max, if it started at 0 for some odd reason, if our, let's say our motion was, we started recording at 0 for some reason, if we did that and our function looked like this, then what we would have is that y at time 0 is 0. And therefore, y is equal to y max cos omega t plus phi is equal to 0. This goes away, and we get cos of phi is equal to 0. And therefore, phi is equal to arc cosine of 0. Or what is phi when cosine is 0? Well, that could be pi half, that could be 3 pi half, that could be negative pi half, on and on and on and on. We would choose either pi half or negative pi half, depending on what the velocity is doing. But we see that our wave is increasing, and therefore we choose the positive value. And this is why I get mad at your book. Your book says that x is x max times cosine of omega t plus phi. If you have a plus, this has to be negative pi half. Normally you write x max cos omega t minus phi, and then phi is pi half. Here phi is negative pi half. Because sine is actually off, it's actually a shifted cosine function shifted by negative pi half. Okay, so it's a cosine function would normally start here. It's starting back by pi half rads. Now, if for some reason your function started at 0 but went like this, you're back 3 halves. So you're at negative 3 halves phi. But really, what's going to happen is you're going to have two cases here. You're going to have the case where it starts at a maximum value. Let's do 3 different cases. It starts at negative max, at positive max, so 0 max, max, and 0, and this is negative. So we could have a function that looks like this. We could have a function that looks like this. Or we could have a function that starts at 0. Now let's see if you understand this, okay? So phi here is going to be when cosine, arc cosine equals 1, because y max, y at 0 is y max, which is y max cos omega t plus phi. Now, since this is 0, I get cosine of phi is y max over y max, which is phi is arc cosine of 1. Here and here I get, this is negative y max is equal to y max. And I'm going to just leave off the omega t. So this becomes negative 1 is cos of phi, and phi, which is equal to arc cosine of negative 1, is pi. So here our phi is pi when it starts at negative, at the negative amplitude. And when it starts at 0, we get that 0 is y max cos of phi, or that cos of phi equals 0. So therefore phi has to equal pi half with a negative sign if you're using a positive sign here, or so that's either y is y max cos of omega t plus phi, as your book writes, it's negative phi, or negative pi half. If y is y max of cos omega t minus phi, as it should be, then phi is pi half. And I'm sorry, that's just a problem your book has that you'll see when you do wave equations comes up. It has to do with the direction of the wave. We're assuming the waves are traveling in the positive direction, and therefore it should be a negative, but your book has a positive. I can't do anything about that. But we've now figured out what phi is, because when we look at our data, we know that our period starts at a maximum value. Therefore, if it starts at a maximum value, phi is 0. and we can write that in here. Our phase angle is 0. Once we do that, the equation of the motion and the equation of the acceleration. Now the equation of our motion, remember, is y max cos omega t minus phi, but phi is 0. So what we get here for our equation is y max is 0.1189 times cosine of omega t, which we said was 7.364 times t. Times t. That is our equation of our motion at any time. Now, our velocity and our acceleration, we can find, once we have y, and this is why we find it, once we know y max cos omega t, v is the time derivative of this. The derivative of cosine is negative sine times the interior. So negative omega y max sine omega t is our v equation. And a is negative omega squared y max cos omega t. Okay, so going back to our worksheet, this is negative 7.3642 times 7.3642, which is omega squared, times our maximum, our amplitude, 1.89 times cosine of omega, 7.3642 times t. So those are our two equations. We're going to need b as well. I can just copy and paste these in. And paste. And this is negative omega 7.3642 times x max 0.1189 times sine of omega t 7.3642 times t. And now we have those. And now comes the fun part. Now comes the part where we need to justify this. So as I said, this is my y equation. Copy it and paste it right in here. I'll put equals, paste that, and instead of t, make sure that you put the adjusted time. Once you do that, you should get your maximum value if your equation's working. Go all the way down. And now there's something important that I need to show you before I do anything else. Whenever this finishes. Okay, so what we're going to do now is we're going to look at the actual data versus our theoretical equation of motion and compare the two. So take column F, G, and H, and all you have to do is highlight all three of them. What it's going to do is when we graph it, it's going to graph both of them against T. So insert a new. And now what this actually is this is y and y equation versus time. Now, this graph I do want you to keep. Copy it, go to that Word doc that I said to create, paste it in eventually. And let's look at this. So the y equation is actually the orange line. And you can see where our orange line, if I got rid of series 1, if I didn't have it on here, you can see it's like a perfect cosine wave. Our blue is our actual data, and it doesn't exactly overlap. It kind of does, but it doesn't exactly overlap. It shouldn't, because real data has discrepancies. In particular, there's a little bit of weirdness here where it seems to be pretty good at the top and kind of low at the bottom. We could actually fine tune this a little bit by adjusting our Ymax and our omega, and it would change this. And I urge you, if you want, play with it a little bit. See if you can get it to exactly overlap to where you don't see any blue. I don't think you can, because real data doesn't follow an exact cosine, but it's pretty good. So going back to this, we've now got our data table that I want you to include that in the worksheet. You got your period. From your period, you found, well, let me go back here. We want this equation, specifically, we want to find Ymax, we want to find omega, and we want to find the phase angle. And this is what you do. You have a homework problem with a blade of a electric razor that's going back and forth. You need to find the amplitude. However far it travels, if it travels 10 meters between points, half that distance is your amplitude or your maximum value, as seen on this graph. For the period, so the amplitude, Ymax, is half that value. And what we did was we inspected our data and found the maximum value, and that was 0.1189. But if you were given that it traveled from maximum to maximum value was 0.23, 78 or whatever, you would divide that in half, and that's your maximum value. We needed to get omega, and omega we found from this equation for t. T, the period, is 2 pi over omega. So all we had to do was look at our graph and find the time of one period from crest to crest. We could have gone from here to here, here to here. We could have gone 1, 2, 3, 4, well, 4 periods here. So not counting the first one, 1 period, 2 period, 3 period, 4 period, and divide the time by 4, whatever. As soon as we have the time of the period, though, we have the angular frequency using this equation. Plug that in, and then the last step is a little bit harder, and that's you need to know where does the motion begin, because that's going to offset your cosine function. We started at a maximum value, and when t is 0, if cosine is a maximum, this needs to be 0 inside. And for it to be 0 inside, phi has to be 0 inside for Ymax to be a maximum. Had we started at the negative maximum, at t is equal to 0, this cos of this argument has to be -1. So we'd have to start at pi or negative pi, either way. Whether you start at pi or negative to pi depends on which way the velocity is going. I don't really care about that. That's not as important to me. My real issue is that you understand that phi is the offset of the function at time 0. Okay, we have no offset, therefore our phi is 0. Once we've done that, we have these things. We can write our equations, because this is Ymax times cos of omega t. This is negative omega, Ymax sine of omega t. This is negative omega squared, Ymax cos of omega t. And we're done, except for looking at the velocity and the acceleration. So I'm going to copy this just to make my job a little bit easier. Don't do that. Oh, what just happened there? I'm going to have to put this back. Sorry. 0. What did I say? 1189 times cos of 7.3642 times t. 642 Remember when you do this, sorry, my brain is a little fried right now. 3642 times the adjusted time. And this equation is negative, well, equals negative 7.3642 times 0.1189 times sine of 7.3642 times the adjusted time, or you could use that next one, whichever one. And then for the A equation, I don't know why I had them do that there. All I need here is this equation, but I'm going to multiply it with a negative sign in the front. So I'm just going to copy that for a second. I'm going to write equals, stop. Right, equals, I'm going to paste that, but I'm going to put at the front negative 7.3642 times 7.3642 times all this stuff. And okay, so now I want you to look at something. And I want you to do two things here. So there's that. I want you to copy this and paste it here. And then I want you, no, don't do that. Sorry, delete that. I want you to copy this column and paste it here. And then I want you to copy this column, paste it here, and drag this one down. Why is my V equation wrong? Yeah, it's doing something weird. I think it changed the, you have to watch with Excel because it changes what reference cell is in the equation when you do that. So let me double check that I have the right on both of these. This one is the same as this, but this can sine of, make it sine of S3. And then you'll see what we're doing. Okay. This needs to be, that is right. And this needs to come down. And you're going to see what's happening here as soon as I'm done posting this. Okay. So what we need to post, or what we need to make, is a graph of V versus Y. So select I, J, and K. Make sure that the equations are correct. And we're going to see something kind of cool. Insert a graph. Now, you can make this as big as you want, but notice the scale here. What this is this is your Y equation and your V equation versus T. Which one's which? Well, we know at time, when time t is equal to 0, y is at its maximum value, while v is at 0. And as it's falling, immediately, starting from maximum value as it's falling, it should be getting more and more negative velocity until it passes through 0, where the velocity slows down and goes back the other way and begins to increase and become more and more positive until it gets to a maximum value when it crosses 0 again and stop. That's what the velocity is doing. The velocity is 0 when it's at a negative maximum, at a positive maximum, and a positive maximum. We already know that, though. That's oscillatory motion with energy. It has all of its kinetic energy when the position is 0, and it has 0 kinetic energy at the maximum and negative maximum points. And that's what this graph is showing you. So copy this one, paste it in your, wherever my stupid thing went. My other one. Where's my other one? Paste it also in there. And then finally, let's look at the acceleration versus velocity. And guess what? It's going to show you the same thing. So it's not going to look too different, but now this is our acceleration versus velocity. And unfortunately, because I moved the velocity to the end, the velocity is now blue here. So when the acceleration, I'm sorry, no, the velocity is now orange here. The acceleration is now blue. But notice something really important. I'm going to actually copy this. I'm just going to call this A and B equations. Copy it. Make sure you label them so that you can remember which is which. And let me put this down a little bit. Now, this was our velocity versus position. This is our acceleration is on the blue, and our velocity is on the orange. I could even put the position on there too. But notice the position is a maximum, and it's about, I don't know, 0.1. And then it's a minimum, and it's negative 0.1, and then maximum negative or positive 0.1. At time 0, the acceleration is negative 6.3 maybe. And when the position, whenever the position is 0, the acceleration has a magnitude that is maximum. I'm sorry, when the velocity is 0. That's because what is physically happening is at the top of the motion, the IOLAB has a maximum negative acceleration, and it has a maximum positive position and 0 velocity. As it falls and passes through the position when it's 0, at that position, the acceleration is also 0, but the velocity is a maximum negative velocity. As it continues to fall, the spring's pulling back on it, slowing it down. The acceleration is getting greater and greater and greater in the positive direction until it's its maximum value in the positive direction when the position is at the greatest negative position. So position and acceleration have a sign difference and they have a magnitude difference, but the signs flip between position and acceleration. And for position and acceleration, when the velocity is 0, they're at a maximum magnitude. And when the velocity is a maximum magnitude, the acceleration and the position are at 0. And that's what these two graphs are telling me. Okay. So what I want you to do is I want you to make those, make that data table, make the velocity, make the acceleration, and do that. Now, we can get the spring constant from the omega. So I don't know if you remember when you did your spring lab, but if you did it, you should remember. We said that omega was 7.3642 rad per second. Omega squared is equal to, omega squared is equal to k over m, and therefore k is m omega squared. Now we know that M is about 0.210 kilograms, the mass of the iLab, 7.3642 squared. This ends up being, if you remember what it was when we did the spring lab and you found it, this ends up being 11.806 newtons per meter. That's pretty close to what you should have found for K when you did your spring lab. Pretty amazingly, or not. So the spring constant on this can be found simply from R omega, which only depends on the period, right? Because omega only depends on the period. It also depends on mass, but I'm sorry, I take that back. I'm doing a million things in my head right now. Omega, which comes from the period, gives you K. But omega only depends on the mass of the iLab and the particular spring constant, which means the period, right? 1 over t squared, which is equal to this divided by 2 pi, right? So I guess I should say approximately within a constant. T squared only depends on the mass and the spring constant. It does not depend on the position of the iLab, the initial position. So it doesn't matter how far I pull this thing down, this iLab is going to move up and down with the same period, no matter how far you begin the initial position, no matter what the initial position is, it will have the same period. If you pull it down further, it's going to travel faster and get more kinetic energy because you're putting more potential energy in. But that's what this next part is. And this next part is totally optional for you. It's for those who want to just play around and explore. We know that the energy for the iLab at any time should be mgy plus mv squared over 2 plus kx squared over 2. So what I suggest, if you want to do the optional part, is create a column of the energy, the potential energy, a column of the kinetic energy, and a column of the spring energy. And when you do that, compare those and look. And what you're going to find is something really messed up. If you look at that percent difference, just if you want to, you don't have to do this. But there's a small problem with our iLab. And in fact, there's a problem with our motion here. We're assuming this is the equilibrium position, but we have mgy and we have ky squared over 2 and we have mv squared over 2, all that energy. We also have a force mg and a force ky. Now the equilibrium position isn't 0. It's the reason why it's not 0 is at any point this thing has a force on it of ky and a force on it of mg. But once it gets to a certain point, this spring's going to start pushing it back the other way. So this is as it's falling, and as it's rising, it's got ky and mg pulling it down. Therefore, it's not just a spring on a table where we can say, oh, this is x is equal to 0, and this is x max negative, and this is x max positive. What it ends up being is that between x max negative and x max positive, this is not, the equilibrium position is not quite at 0. And so when you do that and you look at the energies are going to be different at all times. You're never going to find a point where when the spring energy is 0, all the energy is mgy. I mean, you will, but that's not going to be when the position is 0, which messes everything up. So I urge you to try it. As I said, It's optional, but if you want to try and play around and figure out the energies, you certainly can. You have the data there. It will take 5 to 10 minutes to write an Excel script and get the energy at each different time, compare them graphically to each other, and look at what they are and see if you can find the equilibrium point. The point when this thing is out of position, at what position is there zero spring energy? And just compare them, play around. So anyway, all this stuff here from optional down, you don't need to do. And I wouldn't blame you for not doing. I don't want you to do it. It ends up being a cluster and it sucks. But then you need to answer the questions. So does your equation accurately reflect the IOLAB's true motion? And here, all I want you to do to answer that question is look at how your data lays on top of the blue line. Is it essentially following the exact same path? Remember that what we're trying to do here is we're trying to model periodic motion with a function of the form amplitude times cosine omega t minus or plus phi. So what I'm asking you is, does this theoretical equation that we wrote actually truly model real world data, the real world data of the IOLAB? And the answer is, yeah, kind of. I mean, not perfect, but it's okay. Secondly, does the period depend on how far we pull? What causes the discrepancies? What causes the discrepancies is it's not an ideal spring. And the IOLAB, has air resistance and gravity and blah, 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 blah. There's a lot of stuff going on. We could probably add some terms to our equation to make our equation exactly perfectly lay on there. But it's not perfect. And those discrepancies are there because it's real data. Does the period of the IOLAB depend on how far we pull it? I've already gone over that. T is approximately 2 pi over omega, and omega depends on the spring constant and the mass. Nowhere in there does it depend on the position of the IOLAB, the initial position. That is why we, at the very beginning, set this up to be 0. We zeroed out the position by adding 9.81 to gravity, so that gravity wouldn't affect, where the acceleration was. And then finally, the energy equations do not seem to show that energy is conserved, and they are not useful for calculating K. Why? Well, I'm going to give you a hint here. The why is that they're only conserved for ideal springs, and by far that's not an ideal spring. Ideal spring doesn't really exist. They also, if we go back and really look at what's going on here, you can see that the period is actually changing, shortening up. It's only about half by the time you get to 8 seconds. And the amplitude's actually falling off too. There's friction in our system and there's all sorts of stuff going on. But basically what it boils down to is the equilibrium position is hard to determine. And without being able to determine where equilibrium is, it's impossible to find K. So just know that. Then I want a short, and I mean short, like 1 or 2 sentences for each of these. What was the purpose? What was your equation, including the constants? Did the equations accurately reflect your data? And what would you change to make it more interesting? And then lastly, what I want you to turn in is the data table for part 1. So this one that I filled out, just wherever I put it. Copy and paste this one. The graph of y versus y equation of time. So when we did this y, by taking a plus g divided by omega squared, and this y, and we got this graph that has the two laying on top of each other, I want that graph. I want the y versus acceleration, and I want the a versus v, or whichever way I did it. basically what I want is either A versus Y or A versus B and B versus Y. I think this should really be B versus Y, but whatever. The question's answered and the conclusion. So hopefully that only takes you, I don't know, maybe an hour if you're really struggling messing with the Excel file, if you're not good with Excel. But the data is all there. The main takeaways are that when you have an oscillating system, and here we had the IO lab bouncing up and down under gravity. We pulled it down, we let it go, and we got this position graph. We can describe this position graph using an equation, y max cos omega t minus phi. In order to do that, we need to find y max. We find that usually from the graph, unless we're given the total displacement, and then we take half of that. That's what you're doing in that homework problem with the razor blade. You're taking half the distance that it travels. You find omega from the period. So 2 pi over the period gives you omega, but the period is crest to crest or maximum to maximum. And then finally, you find phi by where does it begin at time t is equal to 0? What is the offset when t is equal to 0? And remember that if it's starting at the maximum positive value, phi is 0. If it's starting at the negative maximum value, phi is pi, or negative pi if you're using plus phi. And if it starts at 0 for some reason, it's pi half. And that's usually the only cases. I mean, you can find other cases, but that's all I wanted you to do. And then the rest of this is just to prove to you that that theoretical equation actually does model the data really well. It's not something that we made up. We're looking at real data and we're modeling it. We're modeling this real data with an actual cosine function. And that is really, honestly, the name of the game here. If we can model the motion of a system, in this case, we're modeling it y max cos omega t plus phi or minus phi, whichever way you want to say it. We're modeling it on a theoretical equation, and we're seeing that it kind of sort of matches it. And that's the whole point of this whole class, to be honest with you. This whole class was about modeling motion with mathematical equations that are based on physical quantities. The physical quantities here were the amplitude and the period. And it does a pretty good job. Although in the real world, like I said, if you were trying to cure cancer, the fact that this period is falling off so fast would tell us that something else is going on and that this is only a good equation for the first 2 or 3 periods. It only matches the first 2 or 3, maybe even not the first one, because you can tell this first one was really jagged and rough when I pulled it down. Anyway, if there's any questions, let me know. You can always text me. I'm going to right now open a submission for this. It will be due Tuesday night. You can do it as a group. You can have someone do it. But what I wanted you to do is go through it and really understand how to use this graph to get this equation, because you're going to have to do something similar on the final, in all honesty. And I think this is actually really, really useful for you to do on your own. Even if you're doing it as a group, at least double check your group members' work. And I know some of you do that. I get texts saying, "Hey, my group got this. I checked it. I'm not sure about this," and I usually explain it. So hopefully it's useful to you and it's not just busy work. But it is a lab grade. And if you have questions, let me know. I hope you guys are all safe from the fires. Make sure you check your grades and go over them with me next week when we review. Make sure I get everything listed for you and you know where your grade's at. And if you have questions, we can talk about that next week. But otherwise, if no one has questions, I'm good. This is all I wanted you to do. Thank you, guys. You too, Alexis. Tiffany, if you want to stick around, you can stick around.